Okay, welcome to 310, Stat 310. This is lecture 4. So today we're going to finish our review of the 309 material that we discussed. So in particular, we're going to finish our discussion on the central limit theorem and go through one or two examples with the central limit theorem. And then we're going to move on to the new material. So this is really the beginning of what is material that was not covered in 309 or equivalent. And it's the start of the material that will be new in this particular course. So in particular, we're going to be talking about distributions related to the normal distribution, the chi-squared, the t, and the f distributions. And this will be covered, this is referring to sections 6.2 and 6.3 of the textbook. So you can find the relevant material from today's lecture in these sections of the textbook. And I should also alert you to the fact that there's a section on the weekly schedule or the outline of the topics that covered, and they refer to sections in the book. So you can also look that up to kind of give a sense of where we're at in the course. Okay, and then just one quick announcement again. Just a reminder that this week's homework, so homework 1, is due Thursday, September 10th. So make sure you get that in on time. Let me know, myself or the TA Chixian, if you have any questions on that. So just to recall what was covered in lecture 3. So we finished talking about the one of the things we covered was the law of large numbers, and the setup was that you have a bunch of independent random variables where you have the expectation is the parameter mu and the variance is sigma squared. And then the law of large numbers asserted that if you take the sample mean, which is 1 over n times the sum of the xi's, that converges in probability to mu. So this is a pretty useful result to kind of say that the sample mean eventually converges to the population mean. But a key thing that's really not covered in this result, and that's something that people in practice really care about, is how fast is the convergence, or more precisely, how close is the sample mean x bar n to mu for different n. And the law of large numbers really doesn't help us with that at all, and that's one of the key reasons why we need the so-called central limit theorem. So for the central limit theorem, we have x1, x2 are independent. Once again, we have the e of xi is mu and the variance of xi is sigma squared. And the central limit theorem asserts that if you multiply by square root of n and then subtract x bar n from mu and renormalize by sigma, you converge to a standard normal. And so this is kind of a pretty surprising and cool result, because we're making no assumptions about the distribution of xi other than its mean and its variance. So let's, as I mentioned, we often will revisit the example involving normal random variables, and we'll do a sanity check to see if this makes sense in the case where we have normal random variables. So if you have x1 through to xn is normal mu sigma squared, clearly e of xi is mu and variance of xi is sigma squared here. And then we know from past lectures a number of times that x bar n is distributed normal mu sigma squared over n. So this is the distribution of x bar n, and we know this because for standard normals, linear combinations of independent normals are normal. And then the other thing we know is that if you subtract off the mean, you still stay normal, because that's again just a linear transformation of the normal, but then the mean's then just going to become 0. And then if you divide by if you divide both sides by the standard deviation or the variance, you're just going to get the standard normal. So what we have here is the standard deviation here is sigma over square root of n. So if you divide by that, you get the expression that we exactly see in the central limit theorem, that square root of n x bar n minus mu over sigma, it actually converges to normal 0, 1. So therefore the central limit theorem trivially holds if we have that these x's are normal mu sigma squared. So in fact, if the x's are normally distributed, we have this result exactly, and it's not even a result that's a convergence and distribution result. But what's very remarkable and very important and useful about the central limit theorem is that it holds like regardless of what the distributions of the xi's are. So that's what makes this result quite powerful and in some ways quite surprising. That we have that, you know, regardless of what the distribution is, as long as we know that the e of xi is mu and the variance of xi is sigma squared and that they're independent, we're going to converge to the standard normal. So, for example, we used this in the first lecture, and so I used actually the central limit theorem results in the first lecture. If your x1 through to xn is a Bernoulli p random variable, so it's like the voting example where p is a probability of voting for Democrat or Republican or whatever else you're interested in, then you can apply the CLT. So what we would get for the CLT in that case is that square root of n times x bar n minus p over square root of p times 1 minus p, that's going to converge in distribution to normal 0, 1. And the reason that's true is recall that you can recall that mu is equal to p, e of xi, and sigma squared is variance of xi, which is p over 1 minus p. So let's I'll just quickly just mention about the proof. Okay, so let me just... So the proof is the proof's quite technical. You may have seen a version of it somewhere. And if we use what's called moment generating functions for distributions, we can prove convergence. So I'm not going to prove it, and I know that some of you may have covered moment generating functions, but some of you may not have. So if that term moment generating function doesn't mean anything to you, that's okay. I'm just talking about how you would prove the central limit theorem, and you can prove it using the moment generating functions to show convergence in distribution. But if that doesn't make any sense to you, then that's okay. It really stems from the mathematical expression of the normal distribution to show to show the convergence and distribution results. So that's just an idea of how the proof works. So we're gonna essentially look at the same example that we looked back in lecture 1. Now that hopefully you're more familiar with the central limit theorem, just so that we're so hopefully it's not maybe as much of a mystery for those of you who it was mysterious to in the first lecture. So we had that. So the setup there was we have that, if xi is the indicator of whether someone will vote Democrat or not, xi has a Bernoulli p distribution, and we use the number that p is 0.55, so 55% of the population vote Democrat. And again, this is a highly inaccurate number. It's just a number that I'm using here. So we have... So we have a sample of 100 people, and then we know, and what we want to say is that okay, so if we have that the sample mean here, so that exactly 50 people in the sample vote Democrat, we want to find the probability that that the number of people in the sample is basically greater than 50. So this is what we want to find, and we're going to use the central limit theorem. And so let me just make it so the central limit theorem is an asymptotic result. So how do we make use of that? It's often called the normal approximation. So what we have there is that so what that means is that if n is large enough, we can kind of say that that asymptotic result is more or less approximately true, which allows us to use the to make use of the CLT. And this is often referred to as the normal approximation, where even though the distribution of x bar n is not exactly normal, we say that it's approximately normal. Okay, and so then what we have here is that we can say that okay, and then we have that okay, so p times 1 minus p is going to be roughly, point 0.24, and then when you take a square root, you'll get back about 0.5. You can do this calculation yourself. And then what we're asked to do is find the probability that x bar n is bigger than 0.5. Okay, and so this is the point where I'd ask you to pause the video again and try to finish off this calculation yourself. Okay, so I'd say pause the video here and for about 5 minutes and try to finish that yourself, or maybe even less time than that. Okay, so now we're back. So we just need to show that the probability x bar n is bigger than 0.5. And so what we want to do is to use the normal approximation. So we kind of want to massage the expression, the x bar n expression, so that it looks like what we see on the left hand side for the normal approximation. And so, like all things in math, what we do to one side, we have to do to the other. Okay. And here we have that n equals 100, so we're going to just have okay. And this is where we can use the standard normal here. So this is, I'm going to use the notation z here to denote a standard normal random one, and this is the probability that z is bigger than -1 here. So that whole right-hand side just becomes -1. And if you look at the standard normal curve, this is, again, we're going to be using the z-score here, or the z, you'll need to use the z-score or the z-table here. We're looking for this area under the curve here. And if you look that up, that's going to be approximately 0.84. So should not be a distribution here. Okay, and so that addresses the question. And again, this is identical to what we did in the in lecture 1, but now we're doing it having covered the central limit theorem and the normal approximation. So to summarize, we have the CLT, which asserts that 0, 1, and the how we use this result is the normal approximation, which is that provided that n is large enough, and I mean, this is a vague statement because what does large actually mean? There's not going to be any vagueness in the course. Like if you're required, if you're required to use this result, it'll be made very clear that n is large enough to make this this approximation good enough. So this is how we use the normal approximation. And this is one of the key reasons why the normal distribution is such a useful distribution in probability and statistics. Okay, so we've completed our very fast review of 309 or relevant 309 material. That's hopefully a segue into what we're going to cover in this course in 310. So as I mentioned earlier, if a number of these concepts are not useful to you, are not sort of clear and something that you're comfortable with, I would use this as an opportunity to potentially go back to your 309 notes and see to make sure that you understand everything. So in particular, I've done a lot of calculations involving expectations and variances, and then covered the convergence of random variables and the various distributions that are important from 309. That should all be pretty comfortable to you. So if it's not, I would go back to that material. Because starting from now, we're going to move into the into the new material for this course, which is and I'm going to start referring to chapters 6 through 14 in the textbook. So this is also potentially a good time for a pause in the lecture just to get yourself ready for the new material that we're going to cover. Okay, so to begin the new material, what we're actually going to do is we've learnt it was 9 distributions from 309 that we'll be touching on throughout the lecture that'll be touched on throughout this course. But there are actually an additional set of distributions, in particular 3 new distributions, which are actually going to be very relevant for 310 for statistics in particular. And these are covered in 6.2 and 6.3 in the textbook. And we're going to see these distributions pretty early on in the course, like as early as chapter 7. These are the chi-squared, the t, and the f distributions. And they're also related to the normal distribution. So you can actually construct all of these distributions from the standard normal distribution. So all of these are functions of standard normal distributions, and we'll see how that's how that's the case. And so okay, and so, why are these distributions useful in statistics? And all we're going to do today is to just learn the distributions, but I'm just giving you a bit of a heads up as to why they'll be useful. We'll see that more clearly in chapter 7 and to follow. And so it's a bit related to why the normal distribution is useful. So we saw that the normal distribution was useful basically through the CLT. So when you want to test if the sample mean, how close that is to the population mean for sample size n, we use the CLT, the normal approximation, and then the z-score. essentially, we're going to be doing similar things with the chi-squared T and F distributions, but there we're going to be looking at kind of different statistics or estimators other than the sample mean. So these are all going to lead to different statistics and statistical tests, which we're going to see in chapter 7 and then chapter 9 later. So that's why these distributions are going to be useful. So for today, the main goal, or for this lecture, the main goal is just to learn those distributions, because we're going to refer to these three distributions later. So let's start with the chi-squared distribution. Okay, so we have that Z1 Z through to Zn are independent standard normal. And one thing to note here is that so what we're stating here for the remainder of today's lecture is these are exact, not asymptotic results. And I just want to make that clear, because the CLT and the law of large numbers, we started really with independent random variables, but the results we were stating were really asymptotic results. But in this material, these distributions that I'm stating here are exact results, which are different, because these hold exactly, not asymptotically. So I just want to make that distinction very clear, so that there's no confusion. So as I mentioned, all of these distributions, the chi-squareds, the T and the F, they're all basically constructed from normal random variables. And so the chi-squared here, we start with n independent normals. And what we're going to do is that let chi-squared of, we'll use this notation n. And I'm just going to write it both in sort of long and shorthand so it's clear to everyone. We're just taking the sum of the squares here of normal random variables. Okay. So chi-squared of n here. So maybe the easiest way for me to state this so that there's no confusion is that chi-squared of n has a distribution of and maybe this is a little bit confusing with notation. So what I'm going to write here is that if you just take a sum of independent normal squared random variables, then that's going to be chi-squared n in distribution. So this is a definition here of the chi-squared distribution. It just comes from the sum of the zi squares. Okay. So like just to be clear about what this means here is that is the random variable, and then is the PDF or it's the distribution. Okay, and so that's just the definition, and again, you can look this up in the book. It's very standard notation. Okay, so let's just think a little about a bit about these properties. So range of chi-squared n. Here we can hopefully see that we're squaring random variables and then summing them up. So we can say that r is, say r chi-squared n is equal to 0 to infinity. It has to be going from, it has to only be a non-negative number. What n refers to here is the degrees of freedom. Sorry about this. What n refers to here, so this you can think of as a parameter associated with the distribution is the degrees of freedom. We'll see soon that that'll be very closely related to the sample size in statistics. We're going to see that over the next couple of lectures. So now let's think about the expectation first. So so we can use linearity of expectation here to look at what the expectation of zi squared is here. So any thoughts on what that is? So remember that zi is normal 0, 1. So we can just, because they're normal and identically distributed, you can just write this n times e of z1 squared. So z1 is normal 0, 1. So what that means is that e of z1 squared is just going to be the variance of z1 plus the expectation of z1. We've got the squared out of the bracket here. The expectation of z1 is just, it's a standard normal, so it's 0. And so this is just going to be 1 plus 0 squared, which is 1. And so therefore we can see that the expectation of a chi-squared n random variable is equal to n. Okay, and now let's, we can also calculate the variance of this random variable. So that equals to the into the variance of the sum of the zi squareds. Once again, we can you can see that we can actually bring this variance inside because we have independence. This is by independence of these zi's. And so once again, we can just write it as n times the variance of z1 squared. So now let's think about what this is by definition. By definition, this is just going to be again, we're using properties of variance here, so this is something that I'm assuming that you're quite comfortable with from 309 knowledge. We'll get back to the expectation of z1 to the 4 here. We know that the expectation of z1 squared is just 1, so we're just going to have 1 here. And so e of z 1 to the 4. There's a number of different ways you can do it. I'm not going to spend too much time on this calculation. I encourage you to go through that yourself. Okay, so this is not something we'll have to do too much in this course. This was something you have to do a lot in 309, but it's not something we have to do too much in this course. But just in case you're missing it, we're gonna just do it once, which is integration by parts. To calculate this this expectation. So okay, so I'm gonna split it up in this way, where u equals z cubed and v prime equals z times 1 over square root 2 pi e to the negative z squared on 2. The reason for that is because v prime needs to be something you can actually integrate, and this allows you to do that. And so by substitution, you can see that this integral works out pretty nicely because of that factor of z outside. Again, if this is not completely comfortable with you at this point, that's okay. I'm just showing you how how you actually arrive at the solution, and it's again just an integration exercise. And so this is going to be equal to u times v. So it's going to be so using the integration by parts, I believe that you're going to get okay. And so you can see that if you plug in both infinity and negative infinity, you're going to get 0 for this expression, because the exponential is going to kill off that polynomial. And this is just equal to the expectation of z squared. And so this whole integral will be 3 in the end. So we have that is equal to 3, and therefore the variance of z1 squared is equal to 3 minus 1, which is 2. And so the upshot of all that is that the variance of the chi-squared of n, random variable, is just equal to 2n. Okay, so we have that the expectation of chi-squared of n is n, and the variance of chi-squared of n is equal to 2n. So that's just giving you a sense of some of the key properties of this chi-squared random variable. And just another thing to think about and give you some intuition is this is actually very closely related to the gamma distribution. So remember, the gamma distribution has a support on 0 to infinity as well. And you can actually show an exact equivalence between the chi-squared distribution and the gamma distribution, and I'll leave that for you to think about and as an exercise. Okay. And I'm just going to make an assertion here that we're going to see in the next couple of lectures that okay, sorry for the technical issues here. Okay, so I think we'll take this time to pause the lecture